All right, good morning, everyone. Thank you very much for joining us today. My name is Dr. Marika Fagan-Endres. I am from the Chemical Engineering Department here at UCT, and I'm supported by my colleague Bridget Clutty, who is our undergraduate administrator, who is going to be helping me with the questions. So as we go through our presentation today, please feel free to pop questions in the Q&A. Bridget will be answering what you can during the presentations, and then at the end we will have hopefully a bit of time, a few minutes, where we can answer some of those questions live as well, the ones which are coming up the most often or maybe the most pertinent. So I am going to start sharing presentation. So as I mentioned, I'm from the Department of Chemical Engineering, and what we're going to cover in the next 30 minutes is a look at what chemical engineering is, because it's something that most people don't know before they actually engage with this question specifically. And I'll spend a few minutes talking about chemical engineering at UCT. We'll have a brief look at our campus and then have some time for question and answers. Okay, so what is chemical engineering? In a nutshell, it is changing raw materials into useful products. And so by raw materials here, you can think of chemicals, of minerals, of gases, really raw materials. And by useful products, we mean things that you would use on a daily basis, things like the water that you drink, the food that you eat, the textiles for your clothing and your furniture, the fuel that you put in your car parts for that matter, your phone, the electronics that go into that, what are they made out of, pharmaceuticals, cosmetics, and the list goes on and on. So basically anything that you can think of in your daily life that you might come across that is being manufactured through a process being the key word, that would have been designed and optimized and run by a chemical engineer. And we do this by understanding how to alter the chemical, biochemical, or physical state of a substance using unit operations. So unit operations is a specific term that we use in chemical engineering, and we'll unpack that a little bit. But what you can also maybe pick up from the statement, so chemical, biochemical, physical state. So we ground our chemical engineering knowledge in the sciences and our good understanding of the sciences, and we use these to build processes. And in addition to this, we need to consider that we have to build safe processes, processes that are sustainable, that use the materials sustainably and that are sustainable from our environment, but that are also cost effective, because no business is ever going to exist where you're going to run at a loss. That's not going to be a good option. Okay, so let's have a little bit more of a look at what we call unit operations. So a reminder being that unit operations are what we use in order to change our raw material into useful product. And unit operations in the chemical engineering viewpoint are generic process stages. So the simplest and maybe easiest to conceptualize are solids handling and liquid handling. So how do we move solids around and liquids around? How do we store them? And then mixing. So how do we combine things? How do we keep them well mixed? Then from a chemical perspective, a really important part of chemical engineering is designing reactors. And reactors are just vessels or containers where reactions happen. People often think of reactors as like nuclear reactors, and that's one type of reactor, but any chemical process that happens will be contained in a reactor. And other examples of unit operations are things such as drying, filtration, separation, extrusion, and so the list goes on. So chemical engineers will be involved in designing how these processes actually look, how they're constructed, and how they operate in when they're all combined into a process. I'm going to use two examples to try and give a bit of context for how this works. and we'll use some really hopefully accessible products. So the first being water that comes out of your tap. Okay, so water, when it's stored in the dams, is not usually straight ready to drink. It's what we call raw water. And that will go through a water purification process to be ready for home consumption. So in the first step, there are some chemicals added, and our water then goes into a basin where it is mixed and we allow a reaction to happen. Okay, so that mixing and that reaction and how that reaction proceeds, that would have been designed by a chemical engineer. We then have a solid liquid separation in the form of a sedimentation basin. We then have further chemicals which are added. And then we have another solid liquid separation through a filter unit. We then add some more chemicals. We then go through what's called a disinfectant basin, which is in our chemical engineering view like a reactor. And then finally some more chemicals, and then storage, where storage also forms an important part of any process, and so is also a concern of a chemical engineer. Okay, so something which might sound really simple, we collect water, we can then use it in our homes, but there's a lot of process that has to happen for it to be safe. And again, a chemical engineer would design and run that process. The second example that I'll use, very topical at the moment, is vaccine production. Okay, so vaccines, it's a very different product to water. It's what we would call a fine chemical or a fine process. It has to be very carefully controlled, very carefully manufactured. So the setup would look very different to a water plant. But still, we would use the principle of unit operations when designing a process to convert our raw materials in order to our final product, our vaccine in this case. In this example, we would start with what's called an upstream process, where we have mixing and reaction in order to get our inoculum ready. We would then have our chemicals move into a midstream process where we use a reactor in order to then produce our vaccine, but which is in a far more complex setup. And then we would then have to send it through a number of what we call downstream separation and purification processes, where we use highly specialized separation steps, each of which are a unit operation, in order to finally get a really pure vaccine that we could use at the end. So we've used here the examples of water and of vaccines, but the list of possible products and of possible processes is endless. So it'll include the basics such as food and drink, anything which is manufactured and isn't straight from, for example, the tree. Okay, that would have gone through a process. And by the way, stuff that comes straight from the tree, in a commercial sense, also would have gone through a process of being washed, being packed, being often preserved in some ways for transport. Again, chemical engineers involved. Water processing, chemical engineers involved there. Energy, production and storage. Mineral processing is a very big topic in South Africa, of course. Pharmaceuticals and linked to that, cosmetics, is a very fine and very controlled application of chemical engineering. Then we've got consumer goods, and that would include things such as soap or toothpaste that you would find in your house. Then you get bulk chemicals, where chemicals are produced for the sake of specific applications. A very generic example would be, things that you would get in a bottle for use in a laboratory setting. And then lots of different specialty materials. And chemical engineers are involved in all of these. Now, what makes chemical engineering a really exciting space to be studying and working in at the moment is the fact that we are in a position where new industrial models are needed at the moment, because we're in a situation where we've got our climate emergency. We're realizing that our raw materials are not infinite, they are finite, and we need to make sure that we use them as effectively as possible, or in some cases find alternative materials, and that means adapting our production processes. And so we want to get to a point where we've got the balance of the economic wealth need being held in parallel with environmental and social sustainability needs. And chemical engineers are at the center of making this change a reality. So defining what we need to produce, how we produce it, and what we produce it from. Chemical engineers are key to all of those decisions. Okay, so now that we've got a bit more of an idea as to what chemical engineering is, we can have a look at how our degree is structured at UCT. So we both have a 4 and a 5-year option. Most of our students, about 3/4 of them, do the 4-year degree option, which is what you automatically enter when you start our degree. In all 4 years, you do some chemical engineering sciences, but there is a progression of sort of the focus of the various years as you proceed through your degree. So our first 2 years are very much focused on building a strong maths and science foundation. And in your first year, you do statistics, physics, chemistry 1, and mathematics 1. And mathematics 2 you carry into your second year. In your second year, you also get to decide which which science specialization you want to follow, which is quite unique to chemical engineering degrees across the country and across the world. So you have a choice of specializing in chemistry further by doing a second chemistry course. You can choose to focus your degree more along the biological, so microbiological routes if you're interested in more of a bioprocess engineering side of things, or you can choose to follow a geological sciences stream, which is very pertinent in South Africa, where we've got very, very rich mineralogical resources. In your second and in the third year of your degree, you then continue to start focusing more on the design of unit operations. So in your first year of your chemical engineering course, you get introduced to a lot of the topics, or you start building up on the concepts. But in second and third year, you really start learning how to design unit operations and how to characterize them. And then towards the latter part of your third year and then your fourth year, you start applying this knowledge that you've developed about unit operations and then looking at how to design and run whole processes and how to integrate them with other considerations that I'll talk to in a second. Also important to note is that in your third and your fourth year, you will see that there is a space for what we call advanced engineering. So you can choose, again, to tailor your degree here towards a number of different specializations. So examples are bioprocess engineering, catalysis, apologies for that, catalysis, or you can do numerical methods, which is more like modeling, or computer modeling and simulations. You can choose to specialize in sustainability or in energy systems, and of course, mineral processing. The blue blocks indicating electives are electives that are outside of the engineering space. So we have built into our program a requirement that our students take a language while they're at UCT, just one language course. Our students are also required to do a humanities elective, of which there are many, many different options. And then there is also an opportunity to do what we call a free elective, which is really anything of your choice, whether it's that you want to deepen your knowledge of a particular topic, or you want to do something entirely different for interest's sake or for fun. Now, alongside the key theoretical concepts that you build in your degree at UCT here, we have a couple of what we call strands, but they're kind of like themes or topics that we work to develop throughout the years of our degree. The first of those is project work, which we believe in our degree, or that we use in our degree, in order to really embed and strengthen theoretical concepts. But we also use projects in order to specifically develop complex problem-solving skills, creativity, judgment and decision making, where these are all incredibly important for chemical engineers to have, or important skills for them to have. Teamwork and communication are developed alongside these projects with particular taught inputs into these. We also spend a lot of time developing a knowledge of health and safety processes, because with any process there are risks involved, and we want to make sure that we are minimizing those risks, both for plant personnel as well as communities around us. We learn about the economy, the environment, and social impacts, as well as interactions with the chemical engineering discipline. And then finally, we spend quite a lot of energy and time developing computing skills. And this is because, computing, the ability to model things on a computer, to analyze things on a computer, and to simulate processes on a computer has become a really important skill for a chemical engineer to have. Now, what I wanted to take a second highlighting on this slide was that a lot of the skills that are developed both in the main theoretical aspects of the degree, but also through these strands which are built across the degree, so like the communication and the computing and the teamwork, they are all skills which have been identified as the top skills needed for the fourth industrial revolution. So things like the complex problem solving, critical thinking, creativity, people management, etc., as you can see on the slide. These are all skills that chemical engineers have as part of their arsenal. And as a result, our graduates are not only sought out by the traditional chemical engineering employers, but also employers across the board for these for these skills that they have developed during their degree. The degree UCT is quite unique, both in the South African context as well as in the world. It applies the best principles and curriculum design that are in place at the moment. It does this through the fact that we have chemical engineering that really chemical engineering knowledge and fundamentals which build throughout the years, with this project focus used to instill the theoretical concepts. The degree is accredited by EXA, which is the Engineering Council of South Africa. And what that means is that once you have finished our degree, you can work anywhere in South Africa, as well as pretty much anywhere throughout the world, because EXA accredited programs are also accredited under the Washington Accord, which allows you to work in the United States or in Europe or pretty much all of the countries around the world. We also uniquely have this ability to tailor degrees according to your specific science interest, as well as that elective space that I talked about. We have inbuilt into our program additional support structures that run both during the term time as well as during the vacation periods, in order to make sure that our students have the best chance possible in order to finish their degrees in minimum time. And overall, we have a really high success rate in our degree of around 80%, which is really high for any university degree, never mind a challenging engineering degree. And then we really work to produce well-rounded graduates that, as I mentioned, are appreciated both by our traditional employers as well as by many other employers out there. Now, all of this is supported by an excellent team of staff who are both really excellent at the teaching side of things, but also who are recognized internationally for their own research and special skill sets. And if you want to learn more about what our staff do and the type of research that we do in our department, I encourage you to go and look at our website and on our Facebook and LinkedIn pages to see the type of topics that our staff are experts in. We also work hard to foster strong industrial connections. We do this, for example, through things such as our Industrial Advisory Board, but also through our research collaborations, as well as our things such as field trips that our students go on. And then finally, we have a really amazing building and lecturing setup. I'll show you a video in a few minutes so that we can have a look at that a little bit more. But really that are top class, both in the South African context as well as in the global context. We are on par with the top chemical engineering departments around the world. Then the nitty-gritty, what do you need to have achieved in your matric or whatever your program that you're studying at the moment at school in order to enter chemical engineering at UCT. So on the if you're doing matric, which is the easiest to describe, you need to get at least a mark of 80% for mathematics and at least a mark of 70% for physical science. Okay, students who get less than those are not offered places in our program. Then you need to calculate what is called your faculty point score, which is basically the mark that you get for your English course, your maths course, and your physical science course, plus your 3 other best subjects. You add those all together. And if you get a score of more than 500 points, you are guaranteed a place in chemical engineering at UCT. If you get what's called a weighted point score of 480 points, that you have a very likely admission, and I say very likely admission because it is very likely, into chemical engineering at UCT. Or at the lower end, if you fall into what we call band C and you get a point score of 420, there is a possible admission into our program. Okay, anything less than 420 and you would not be offered a place. Okay, so before we go to questions and answers, I'm going to show you a quick video. Hopefully this works, just because we're doing this virtually, so that you can get a look at our buildings and our lecture theatres. Okay, so there you got to see a little bit of our building that we have. It was built fairly recently in the past few years, and yeah, so as well as our lecture theatres at the end, where you could see the environment that our students work in. Our students work mainly on laptops, and we have really fantastic spaces for our teaching to happen in, as well as our prac labs. Okay, so a reminder that if you want more information, we are online, so we have our website that is you can find via the UCT website. We also have a LinkedIn page, an Instagram and Facebook, so that's at UCT ChemEng, and you're welcome to browse through those to see news stories of what we're up to, what our students are up to, and what our researchers are up to. Okay, and that brings me to the end of my presentation. So according to my watch, we've got about another 5 minutes left where we can deal with some of the questions that haven't been answered already by Bridget. So Bridget, can you come in and maybe tell us what students or what our potential applicants are wanting to know about our degree?
Yes, there were a few questions. Can you put it on, see it on the published side? Regarding the science stream, would the chemistry 2 be more beneficial for ChemEng 3?
So we set up our degree program so that whatever you choose as your science specialization is not prerequisite knowledge for whatever courses you have afterwards. So we require that you do Chemistry 1, and that gives you enough information to handle all of the subsequent chemical engineering subjects. Chemistry 2 is really if you are interested specifically in deepening your chemistry knowledge, so that maybe one day when you went into working as a chemical engineer, you would want to be working along those lines, that skill set. Yeah, so it's the same with like if you chose a biological sciences route, chemical engineering 3 would not require you to know about microbiology, and the same for geological sciences. Yeah, anything that maybe was drawn on from those topics would be taught again to make sure that everyone was up to speed and on the same page.
Okay. I have answered the minimum requirements, which I just copied a link from the website. Marek has already covered that.
Yeah.
Next question was, is it easy to get a job being a chemical engineer?
Yes, so I mean, students always have a period where they search for jobs afterwards, but our students have really high success rates in finding jobs afterwards. And if you're interested in where our students actually end up working, there I think was an Instagram post on that last year or the year before. They end up working across different sectors and fields. Yeah.
Okay, does chemistry 1 stream involve biology?
No, so chemistry 1 is just chemistry. So it's an extension of what you would do chemistry at school.
Okay, next is, okay, do students get engineering overalls? I assume that's the lab coats.
Yes, so in order to be able to do any work in our laboratories, there are certain what we call PPE, which is personal protective equipment you have to wear. So that's lab coats, lab goggles, and then we require closed shoes and long trousers. And that's sufficient. And we've got setups at the university in order to provide access to those.
If my grade 11 results meet the requirements, but my grade 12 don't, will I still have an opportunity to be accepted?
So before your final matric results come out, if you meet our minimum requirements, you will be given what is called a conditional offer. So you're looking really good, we want to offer you a place, but that conditional offer will be conditional on the fact that your matric results do meet our final entrance requirements. So that's, yeah, it does have to be a requirement met right at the end of your matric.
So next, do we need to write NBTs?
So that information, the best place to go for that is the UCT admissions website. It's not a published requirement for our 2023 places as far as I know, but admissions websites to confirm that.
What would be the specs for a laptop needed for this degree?
Mm-hmm. So every year we review those specifications in order to make sure that you can run all of the programs that we need on it. And before you start, if you were offered a place and before you started with us in sort of the month or two before, we would send out a letter specifying what those requirements are. It's generally something along the level of an i5 processor, but as I said, those requirements are updated on an annual basis. But it's a fairly standard laptop spec. And sorry, Bridget, it's also worthwhile mentioning that in our final years of study where we used more specialized design software, we have got our own dedicated what we call design studio, where our students have access to computers that are dedicated for their use for those programs and that can run it. So even if the laptop isn't quite up to scratch, we've got you covered. Bridget, I see, according to my watch, we are now at past, so I'm sure students are going to be running off to other presentations. So maybe we leave it there for today. And I want to thank everyone for joining. And as I said, if you've got more questions, please visit our website or contact myself or Bridget for more information. Bye, everyone.
Bye.